The way they're building it right now is a little bit academic style. We need to build it much more in the way, let's say TSMC builds it in Taiwan. I do like the idea that he started this kind of at the end of his career, focusing on hardware and doing that right. So I kind of appreciate what he has done.
So after you left Google, you started your own startup, Qolab, in 2022, right? So what does the company do? I think we probably touched it before. I would like to know, what do you want to achieve?
Well, the overall goal is to build a useful quantum computer. When we were at Google with the quantum supremacy, we built a powerful quantum computer, but we need to make it useful. Now, one of the ideas is to build a general purpose error-corrected quantum computer. That's about 1 million qubits. I'm going to say the technology to build that, you would build a 20,000 qubit quantum computer, and if you didn't need error correction, that would be the right way to build it. So it's a general way to build the quantum computer. Now, to do that, we believe the key technology that's needed is to build qubits with advanced manufacturing processes. The way they're building it right now is a little bit academic style, if you like, and we need to build it much more in the way that, let's say, TSMC builds it in Taiwan. We don't need quite the lithography needs, but we need to use the advanced processes of deposition and etch, as opposed to simpler process of liftoff. So we've been working on that since there. We have lots of ideas on how to make that better, and we're progressing towards making these new processes in order to build the qubits in a better way.
Since you talk about TSMC, so it reminds me back in around like the 1980s, Morris Chang, who founded TSMC, he created the foundry model. One company can focus on manufacturing and others can focus on IC design. So is it similar that you are doing?
Yeah, I would say it's similar in the sense that we don't want to raise the money or to do that to actually build the chips themselves. The most advanced processes, the tools are very expensive, and we think that's kind of not the way to do it. Our company is more the qubit designer, but also we need to know a lot about the fabrication process. So when we develop a fabrication process, we're kind of developing the process and process concepts, whereas our partner is developing the actual tool usage and parameters that they need to build the process properly.
But for a lot of companies, even huge companies or startups, they are all producing their quantum computers together. They do it their own. So are you playing a game changer right now?
Yeah, so most of the companies right now, and I'm going to take Google as an example, but IBM and Rigetti and Amazon also kind of do the same thing. There's what's known as vertically oriented, where they try to do everything. Okay, and that's the way the computer industry was in the 50s, 60s, and 70s. But and IBM was very successful at that. But what happened is that all the technologies got quite sophisticated, and then it went to what's called a more horizontal model, where different companies were focusing on different things. Let's say a disk drive company, a memory company, the CPU company, various parts of the fabrication were done. And we think that's the better model for the future.
When talking about TSMC, do you know Morris Chang?
I've not met him, and I've read small snippets of his story and know that he created something very amazing. I do like the idea that he started this kind of at the end of his career. It was a Texas Instrument, really focusing on hardware and doing that right. So I kind of appreciate what he has done.
Your route is kind of similar, do you think so? Or
maybe it could be. I imagine, everyone's journey is a little bit different. But yeah, I appreciate that. I'm going to say what's really different about what we're doing, not just in the manufacturing, But most of the companies in superconducting qubits are headed by theorists. And I think you can kind of think about doing that is because it's very easy to abstract the physical qubits into a mathematical object, and you talk about how you would, put algorithms together and the like. But the real problem with qubits is that real qubits, there are defects and problems with the physics. And you have to understand that very deeply in order to engineer everything and manufacture it properly. I think that's our focus, is to really understand the manufacturing process, the physics very deeply, and to guide the other companies in order to build things in the right way. And that's been our role in Qolab, is talking with our various partners.
So you are working on to reduce the error correction rate, right?
We would like to build a system that's forward compatible to error correction. In the beginning, making hundreds or thousands or tens of thousands of qubits is something we see we can do, and we want to build that, but we don't want to build in a way that we hit a brick wall, hit a dead end. So we want to build in a way that's forward compatible. That's what we're doing with our processing. It's more design, but we're also designing the processes. And we also understand the physics, which is very complicated. We have to work very closely with our fab partners to kind of see what the data is telling us, develop the physics models, work on the process. And what's nice is that the partners know a lot about the processing, and we know a lot about the quantum physics of these devices. And we just have to work together to make progress.
Now, currently, there are so many companies building their own chips, right?
Right.
Their own qubits. So, of course, most of them are based on your original work. But when so many players are currently in the market, how does Qolab to stay ahead, to stand out?
I would say there's many players in the market because people can build it themselves. And they're focused on that, and they know how they can improve it by doing that. But like I said, I think all that technology is going to reach a dead end. And there's some fundamental problems there. So we're trying to build a process that can, make everything's better. And then, we can imagine a business model where we're working with a large number of companies to help build the qubits for them and to understand the physics and the design and the processing with it. So there's a lot of different models we can do. We understand that most people don't want to reinvent the way they're making qubits. So that's kind of our job, and that's our special niche in the ecosystem.
Besides your approach, are there any other qubit technology that you think it could scale up in the market?
Well, very recently, people have been looking at neutral atoms, and that has been very popular. And they're talking about making hundreds to many thousands of qubits. There's still a lot of questions in my mind, but they are working pretty well, and they're doing very good research. And I consider that to be a serious, I'll just call it threat to the superconducting qubits. We've been doing well for a long time.
Yes.
Part of my pitch to people in superconductivity is we have this threat, and they're doing fairly well, and we have to really work on fixing the biggest problem with superconducting qubits, and that's making them scalable and making them manufacturable. So in some sense, I think this helps us a little bit, in terms of being competitive. But in the end, I'm also happy that there's lots of other ideas out there and people are working on it. In the end, I would just like to see a quantum computer can be built. I'd like to build it, or I'd like to help people build it. But, if someone else can do that, then I think that's really good for physics and technology and science.
So you like to see the quantum industry prospers, right?
Yeah, that's right. What I try to emphasize, I think building a quantum computer is a little bit harder than people think, especially because you have to get so many things working at the same time. I think we need to help each other a little bit more instead of, competing against each other, and then we can all be successful. But not everyone thinks that way. That's okay. But I think it's very exciting because it is so competitive.
So the numbers of qubits is very important to the success. So some companies set a goal to manufacture 1 million qubits maybe in 10 years. So do you think it's realistic? And does Qolab has any specific goal to achieve or timeline in mind?
Yeah, that's the kind of number and timeline that we're talking about. To get to that, what we have to do is focus initially very hard on manufacturing and manufacturing it in a scalable way, which we're doing with semiconductor companies. And then our hope is once we do that, then we can scale up much more rapidly in the same way that the semiconductor industry has scaled up very rapidly. We can take advantage of all that. And I don't think the physics community has quite taken advantage of that. They're using many of the same tools, but they're still doing things in what I would call an academic and not industrial way. And in the end, it's all about having good manufacturing.
So having a good manufacturers, you need to have good partnerships, right?
Right.
Yeah, that is what I see that Qolab is really working on.
You know, it's Q plus collaboration, so that's in our name. Okay, we decided very early on that's what we have to do. So very much collaboration with, you know, the best technology companies in the world.
So you work with Applied Materials and
Right.
Western Digitals and the quantum machines in Tel Aviv. So what kind of specialization they are providing that you believe is critical for building a quantum computer?
So Applied Materials is a very good collaborator because they're making the 300 millimeter tools with the most advanced processes. That's better because these are very expensive tools. Let's just say $50 to $100 million. And even if you're in a big company, you can't afford that kind of machine if you don't know the process is going to work. So by working with Applied Materials, of course, we have to share in the intellectual property. That way they can retrofit the machines they already have relatively inexpensively to try out the processes and to develop the machine. And in the end, if we have to do some processing with them, for you know, they're used to doing that. They have a research and development lab where they can do very light production runs. So that's an ideal situation for us. The same thing kind of happens with Western Digital. They are used to making these kind of devices, so we can do that with them too. We have a different approach with them, a very complementary approach. So it's good we're looking at this in two ways. When we work with Applied Materials and even others, they know a lot more about the processing. We make something and it goes wrong a little bit. They talk to the experts and they have lots of ideas on how to fix it, and they can do it. Now, it's slower because it's a big production run, the individual iterations, but because of their expertise, we can go faster in figuring things out. And then in the end, when they make our devices, they're really clean and nice and uniform across the whole wafer, which is something that would be very hard to do for an academic lab.
So far in your experiment, it works well?
Yes, things are going well. What I would say is we have to kind of reinvent every step, and there are certain things that are difficult that we have to work around, but things are going very, very well. And we're hoping in the next few weeks that we can start testing the way that qubits and junctions are made in this new way with hopefully getting much better results. So we've been working on this for a while and improving the materials and testing materials for about 2.5 years now, and everything has gone well, and we just have to put it all together. It's difficult when you basically do things from scratch.
So all the efforts that you and the Qolab are working on are making a useful quantum computer, right? So when do you think we will finally see a truly quantum computer that can solve real-world problems?
So everyone right now is talking about something like 8 to 10 years. So, you know, and I think people are being a little bit optimistic. I think we have a plan to stick on that timeline. I think we can do that if we were well funded. So what I used to not answer this question, But what I'm going to say is I think there's enough optimism in the field now that I'm saying somewhere in 5 to 10 years that we can build this general purpose.
Faster?
5 to 10. Now, I think that could be a little bit optimistic because it's, I think, harder than people think.
Yes.
But there are really interesting ideas coming out there. But the reason I give a little bit faster timeline is that if you build this kind of quantum computer, you should be able to break RSA, which is the encryption for the internet and for banking
Yes.
and many, many things. And I think it's good to talk about this possibility so that people are ready to replace the encryption standards. And they've come a long way, and people have, you know, new systems to do that. And people have to be a little bit more cautious about switching over in this thing. It's funny because when the CEO of Google, Sundar Pichai, commented, he says 3 to 5 years. And I think that's too fast. But on the other hand, as a big tech CEO, he has to make sure it's a shorter time period so that he and others are ready for it. So I think that's a perfectly fine prediction for him. I think 5 to 10 is more likely. It may even take longer. But people are coming up with really good ideas, and one should not think that it's going to take, you know, forever to do this. Things are making good progress now.
So do you think quantum computers will do a really good threat to cipher, to blockchain, to...
Well, you just have to use a new protocol for encrypting the data. And you know, the way I like to think about it is encryption systems have been around for, I don't know, thousands of years,
Yes.
a long, long time.
Yes.
And over time, you have to retire some of the crypto systems, and it has to get better and better. And RSA has been around for, I don't know, 40, 50, 60 years. It's been around for a while now. But it's maybe not surprising that it's entering the end of life, and then we just have to go to other crypto systems that'll be more secure. The other thing I've been told, I'm not an expert on this, is that the way RSA was developed, it was kind of patched into certain networks. And then I think people now are looking at a more holistic way to build the crypto systems so that in the future, if you need to change it, it's a relatively small thing you have to change. Whereas now, replacing RSA, they need to work on the architecture of the encryption system to make it more flexible in the future, which is again a good thing. This is clearly something that you know that's going to be beneficial for these systems.
But if we have quantum computers right now, the crypto system probably will be crushed immediately.
Yeah, right now would be a problem, but we don't see that happening.
Yes.
But we don't know. I'm going to say I think it's going to look imminent. You know, like in the next few years, it might happen, and then people have products out there, and then there'll be a big push to change it. The one thing to remember is that these quantum computers, let's say, break RSA, but it takes a long time. I'm just going to say a day. Let's say it takes a day. So you can't break too many systems, okay, to get there. So, you know, it's still something you have to worry about and protect because there's a lot of valuable things out there. But, you know, those are more governments and banks and other institutions. And, you know, they'll be on this first. For the average consumer, we have a little bit more time. But clearly, it's an issue that has to be dealt with.
So let's go back to the useful quantum computer, because you mentioned that fabrication is very important, right? And Taiwan is well known for it. So
Right.
you have worked with Taiwan's Academia Sinica in quantum research for a while. So can you share with us your experience working with the institution? What impressed you the most?
Well, working with Academia Sinica from 2022 to the end of last year was really great. We put money into a fabrication at ITRI,
yes.
and we were able to make some nice qubits out of that and develop the technology. So that was very nice, and it was good working with them. We were also consulting about how to bring up qubits, and it's a very good project. I'm really happy that what's the southern campus that they have, Academia Sinica has developed. So really happy. We hope to be working with them next year in a little bit different, more of a business arrangement, since our company has evolved. So we're happy. I plan to be in Taiwan in February as part of an Asia trip, so I'll be able to talk to people then. That was really important for our project to work with them.
You are kind of familiar with Taiwan, and we do have a reputation in manufacturing, right?
Yeah.
So will Qolab work with Taiwanese companies to manufacture quantum chips someday?
Yes, I think that's quite possible to do. I think the problem right now is you can't take your CMOS fabrication and then make superconducting qubits. There's some specialized steps and processes that you have to develop to get there. So it's not an obvious thing to do, and you have to put some decent amount of funding into it to do it custom. So that's what we're doing with Applied Materials. We're providing some funding. They're doing some self-funding to do it. But the real problem is you have to retrofit existing systems. And if you're in a CMOS foundry, you kind of don't want to do that because it's different. So what I think the way to think about this is we're developing the processes and the physics knowledge and materials knowledge, and then at some point you can envision what that process is, and then it's time to, think about other ways to put a foundry together to do this. But clearly Taiwan has fantastic knowledge for doing this, and that would work fine.
Any advice you would give to Taiwan if we want to have more breakthroughs in quantum computing?
I think it's good that they have, these projects going on in Academia Sinica and elsewhere to build quantum computers, and quantum computers of different types. And you just have to bring up the intellectual knowledge of having experienced people there doing that, because it takes a while to bring up a big research effort, and it's complex. There's a lot of things that involved in this, very subtle physics and engineering challenges. So it just takes some time to do that.
So be patient.
Yes, patience is good. I also would say is that we all want to build a quantum computer and be very successful at that. But I would also look at it as just as training the scientists in Taiwan. You're very good at engineering and business, okay? But to bring up a big scientific community is also a different kind of thinking that needs to go on, and that takes some time. But I would say quantum computing is a really good way to develop the scientific talent. And it may not be you're at the forefront of making a quantum computer, but you are training, the science mindset of the country in a good way, and in an internationally competitive way, which really, pushes everyone to think carefully about it.
I think that is a powerful insight for Taiwan. It's really very valuable perspective. So I think your advice will be very inspiring for the quantum community in Taiwan. Good. John, thank you again for having us in your beautiful home.
And I'm glad the weather cooperated today. It looked like it might rain, and it's been sunny and nice here. So it's great to talk to you outside in my home.
Yeah, and then we hope we can see you next February, right?
That would be great. I'm looking forward to that visit.
Okay. 想要了解更多深入的财经资讯呢，请锁定未来财经投资聊一下，按赞订阅，开启小铃铛。我们下次再会喽，拜拜。